Welcome to the second lecture of this week. In the last lecture we started with hygrothermal analysis of composites. So, at first we looked into the micromechanics, and within the micromechanics at first we found out alpha 1. Alpha 1 was homogenized thermal expansion coefficients along direction 1. So, fiber and matrix have different properties, different thermal expansion coefficients or moisture expansion coefficients. We found out the homogenized one along direction 1. Now, we have to find out the expansion coefficients along direction 2. So, thermal expansion coefficient along direction 2. So, direction 2 means the transverse direction. So, for that we will again follow the same approach that we used for finding out E2. So, first we will find out using the mechanics of material based approach. So, again let us assume that we have the idealized version of the fiber and matrix combination F and M, and this is direction 1 and this is direction 2, and this is under some temperature change delta. So, the stress along direction 2 is sigma 2. Now, in this case our consideration is that sigma 2 is same for fiber and matrix, but this fiber and matrix have different expansion. So, if we say that Tf is the dimension along direction 2 for fiber and Tm is for matrix, and then if it undergoes some expansion, so this is the final delta, that means expansion, and that is equal to delta F plus delta M. That means change in the length for fiber, change in the dimension of fiber and change in the dimension of matrix along direction 2. So, we have seen that stress along fiber, we can write that as, and that is equal to sigma 2 because stress in fiber and matrix are same. So, that we can write as E2 multiplied by epsilon 2 for fiber minus epsilon 2 for fiber free with the thermal the free strain of that. So, epsilon 2 with superscript F, and then with that we can write epsilon 2 F is equal to sigma 2, this is also a 2 F divided by E 2 F plus epsilon 2 F with superscript T, and that again we can write as sigma 2 into sigma 2 by E 2 F plus epsilon 2 F T is alpha 2 for the fiber into delta T. We know that epsilon 2 F, the free thermal expansion, free thermal strain is alpha 2 F multiplied by delta T. Accordingly, we can write that delta F is equal to, the initial dimension of it was Tf. So, Tf multiplied by that strain. So, Tf into sigma 2 by E2F plus alpha 2m into delta T. So, that is for fiber. So, expansion of the fiber, and accordingly we can write sigma 2 for the matrix part, sigma 2 m or sigma 2, that is equal to E2m into epsilon 2 m plus epsilon 2 m with superscript T minus epsilon 2 m with superscript T, and we know that epsilon 2 m with superscript T is alpha 2m into delta t, and then we can write alpha 2m is equal to sigma 2 divided by E2m plus alpha 2m with superscript t, and that can be written as sigma 2 by E2m plus alpha 2m into delta t. Now, if we say that the equivalent coefficient of thermal expansion along direction 2 for the composite is alpha 2, then we can write the total expansion of the composite is sigma 2 is equal to E, we can get that from this equation, and we can write that sigma 2 into equal to E2 into epsilon 2 minus epsilon 2 with superscript T for temperature, and that we can write as E2 into epsilon 2 minus alpha 2 delta T, and then finally we can write epsilon 2 is equal to sigma 2 by E2 plus alpha 2 into delta T. And for the previous case, for the matrix case, now we can write delta m is equal to Tm multiplied by sigma 2 by E2m plus alpha 2m into delta T. Similarly, for the total expansion delta also we can write delta is equal to delta f plus delta m, and we can write this from this equation as Tf plus Tm multiplied by sigma 2 by E2 plus alpha 2 into delta T. Now, we can write this entire quantity as this plus this. So, we write Tf plus Tm multiplied by sigma 2 by E2 plus alpha 2 into delta T is equal to Tf multiplied by sigma 2 divided by E2f plus alpha 2f into delta T plus Tm multiplied by sigma 2 by E2m plus alpha 2m into delta T. Now, we can take this Tm plus Tf here in the denominator, and that gives us, and sigma 2 is then that gives us sigma 2 divided by E2 plus alpha 2 into delta T is equal to sigma 2 divided by E2f plus alpha 2f delta T multiplied by Vf plus sigma 2 by E2m plus alpha 2m delta T multiplied by Vm. Now, we can look at these quantities. This quantity is equal to this quantity plus this quantity. So, we separate that term out because this is equal to this plus this. So, if I separate that, finally we get alpha 2 is equal to alpha 2f multiplied by Vm plus Vf plus alpha 2m multiplied by Vm. So, that becomes the relationship between alpha 2 and the alpha 2s for the constituents matrix and fiber. Now, using the energy approach, Scarpi got somewhat different expression, and that was alpha t is equal to 1 plus nu m multiplied by alpha m into Vm plus 1 plus nu f multiplied by alpha f into Vf minus alpha 1 into nu 1 2, and this again his derivation was for isotropic cases, and for more details this paper by Scarpi can be referred to. Hashin got a different expression. So, Hashin's expression was, so again for that this paper by Hashin can be referred to, and that expression is alpha 2 is equal to alpha 2m alpha 2f into Vf into 1 plus nu 1 to f multiplied by alpha 1 f by alpha 2 f plus we had alpha m into Vm into 1 plus nu m, and then minus alpha 1 to f into Vf plus nu 1 to f into Vf, not alpha 1 to, plus nu m into Vm, and then it is multiplied with E alpha with subscript 1 divided by E 1, and E alpha with subscript 1 is equal to alpha 1 f into E 1 f into Vf plus alpha m multiplied by E m into Vm, and E 1 we already know it is E 1 f multiplied by Vf plus E m multiplied by Vm. So, Hashin's approximation was for orthotropic fiber and isotropic matrix, So, a study can be done with numerical values to see how close are these three expressions in agreement. Now, what we will do is the transformation of CTEs. So, alpha 1 and alpha 2. Again the transformation is between axis 1 2 and axis xy. So, we have a system xy that we use for analysis, and fiber direction is 1 and matrix direction is 2. So, for that let us write the free strains due to temperature or free thermal strains, we can call it free thermal strains epsilon 1, epsilon 2 and 0, because if with respect to direction 1 2 we will not get any shear. So, it is just alpha 1 multiplied by delta t and alpha 2 multiplied by delta t. These are all normal strains. If I just multiply alpha 1 with delta t, I get the normal strain along direction 1. If I multiply by alpha 2 into delta t, if I get strain along direction 2, but we do not get anything in shear. But when we transform this, then we will see that shear will also come. Now, so our goal is to find out these alphas with respect to direction x y, and we will see that when we deal with the coordinate system x y, we will get something called alpha s or alpha x y also, that is alpha corresponding to shear. Now, if I transform these strains, so to x y system, so epsilon x, epsilon y and epsilon s, and to be more appropriate these are all thermal strains. So, these are free strains due to temperature. So, let us put a superscript T and then that follows the transformation law, and that law is m square n square minus 2 mn n square m square 2 mn mn minus mn m square minus n square, and that is and then we at the right hand side we have epsilon 1 T. We can write just those in terms of alpha. So, alpha 1 into delta T, alpha 2 into delta T 0, and also this is tensorial because the tensorial strain vector follows this transformation rule. So, we have to have the tensorial definition here. So, this gives me alpha 1 m square plus alpha 2 n square, and here we get alpha 1 n square plus alpha 2 m square, and here we get mn multiplied by alpha 1 minus alpha 2 and it is multiplied by delta T. So, with that we can write epsilon x, epsilon y, epsilon s temperature as alpha 1 m square plus alpha 2 n square, and here I have alpha 1 n square plus alpha 2 m square, and here I have 2 mn because epsilon s by 2 is equal to this. So, epsilon is equal to 2 mn into alpha 1 minus alpha 2. Now, we can define a quantity alpha x, alpha y and alpha s, so that if I multiply those with temperature I get this. So, this is equal to alpha x, alpha y and alpha s multiplied by temperature. So, that tells me that the expansion coefficient alpha x, alpha y and alpha s is equal to alpha 1 m square plus alpha 2 n square, alpha 1 n square plus alpha 2 m square, and here we have 2 mn alpha 1 minus alpha 2. Now, if I plot this alpha x, alpha y and alpha s with theta, the angle, then the plot looks like this. So, this is 0 degree and here we have pi by 2, the plot looks like this. So, this is alpha 1, and then just the opposite plot is for alpha 2, and this is alpha 2, and in between them we can have so this is alpha x, alpha y and this is alpha s. So, when theta is equal to 0, that means the direction x and direction 1 coincides with each other, that means the fibers are oriented along direction x. In that case alpha x is equal to alpha 1 and alpha y is equal to alpha 2. When the opposite thing happens, that means the fibers are along 90 degree orientation. So, the fiber direction x coincide with direction y. In that case alpha y is equal to alpha 1 and alpha x is equal to alpha 2, and when x coincides with 1 or 1 y coincides with 1. So, that means it is a specially orthotropic ply. So, in that case there is no alpha s, but in between that alpha s can exist, and it is maximum when theta, that means the angle of orientation is equal to 45 degree. Now, the coefficients of moisture expansion so coefficients of hygrothermal expansion, we can not hygrothermal expansion due to moisture only, CHE. So, these coefficients are same as the temperature coefficients corresponding to temperature. So, we can define beta 1. So, beta denotes the CHE, the moisture expansion coefficient. So, beta 1 is equal to E1 into F multiplied by beta 1 into F into Vf plus Em into beta m into Vm divided by E1F into Vf plus E1m into Vm. Now, here again beta represents the moisture expansion coefficients. So, when it is F, it is for fiber, m for matrix, and accordingly beta 2 is equal to beta 1 2 into Vf plus beta m into Vm, and that is from the strength of material based approach, and otherwise we get Vm is equal to nu m, beta 2 is equal to 1 plus nu m multiplied by beta m into Vm plus we have 1 plus Vf multiplied by beta f into Vf minus beta 1 into nu 1 2, and again this relation assumes isotropic and it was given by Scarpi. So, these, and if I look at the expansion coefficients, they follow the same rule. So, beta x is equal to m square beta 1 plus n square beta 2, this is equal to m square beta 1 m square beta 2 plus n square beta 1, and this is equal to 2mn beta 1 minus beta 2, same transformation relation. So far we have found out the CTE and CHE, that the coefficients of hygrothermal expansion both along direction 1 and 2, and we have seen how they transfer. So, now we are in a position to look at the ply level. So, we can relate the stresses with these quantities, and then we can look at the laminate level. So, we will do this in the coming lectures. We will end this lecture here. Thank you.